So lesson 7.2 is called absolute value functions. We're going to look at the graphs of what an absolute value does. So we are going to graph the following, and we're going to use a table of values to determine what the graph is going to look like. So I'm going to start with values that I'm picking for x. So this is x and this is y, x, y. So I'm going to start with -3, then work upwards. So if I substitute -3, what I'm doing is I'm going -3 plus 1 in absolutes, adding 2. So -3 plus 1 would be -2. The absolute of -2 would be +2. And then the negative outside the bracket would make this -2 plus 2, which is 0. So our first value is 0. And we would do the same thing with the other one. So I could put them in my calculator. So there is a button in your calculator for absolutes. So if you go to your graphing calculator, you would press math, and then you would go to the right for number, and it's the first one, number 1, ABS, so absolutes. Okay, so I would plug in -2 into x, so -2 plus 1 is -1, the absolute of -1 is +1, but the negative outside of it would make it -1 plus 2, which is 1. And I would continue with all the values by putting them into the equation and solving for y. Okay, so once I have the values of my x and y coordinates, I'm going to plot them. So -3 is at 0, -2 is at 1, -1 is at 2, 1 is at 0, 2 is at -1, and 3 is at -2. So what you should find is that when it's a linear equation, so if you were to take off these absolutes, it's actually a linear equation. A linear will pretty much always give us this kind of V shape, so we're going to connect them, and this is going to be an upside down V shape. So this is the equation that is created. So the vertex would be this top point right here. So this is the vertex. And our vertex here would be the coordinates of -1 and 2. The domain of an absolute function that is linear would be x such that x is an element of real numbers. And then we have, for our y value, our range, we would say y such that y is less than or equal to the highest value, so it's going to be, in this case, 2 YER. So the graph is from 2 and below. So if you guys notice, your y coordinate lines up with 2, and it goes everywhere below that. So that would be your domain and range. So that would be what a linear equation would most probably look like. And then we have our quadratic. So our quadratic, again, we're going to do a table of values. So I'm going to pick values where I can graph them and see what it looks like. So I'm going to pick values, for example, like -3, same values, -3, -2, -1, 0, 1, 2, 3. So if I plug in -3 into this, -3 plus 2 is -1 squared, which would be 1. 1 minus 4. 1 minus 4 is -3, and then if you square that, -3, and if you took the absolute of that value of that, you get +3. And if I plug in -2, -2 plus 2 is 0 squared, minus 4 would be -4, the absolute of -4 is +4. And I would plug in each of these values and get a number for each of them. Okay, so at -3, I have the value of +3. at -2, I have +4. I have a 0, 0 point. I have the point. I'm also going to find one more value. I actually need one more value. I'm going to plug in -6. So -6 plus 2 would be -4. -4 squared is 16 minus 4. So that would be 12. So that'll be pretty high. So -6 and +12. And I want to find -5 as well. -5, if I plug in -5, I get -5 plus 2. And then I would square that to get +9. Minus 4 would be +5. So at -5, I have +5. And I'll continue graphing the other points. Okay, so I needed all these values because when I graph these, if I plug in -4 as well, so I'm trying to fill in all the gaps just to see where it looks like, what it looks like. So if I plug in -4 plus 2, I get -2 squared, which is 4. 4 minus 4 is 0. So these are my two x-intercepts, so I'm going to need that. So what's going to happen is the graph is going to continue on to the left forever. It's going to go down to touch that x-intercept, and it's going to reach up and create kind of a parabola shape. Then it's going to touch the x-intercept and again go upwards. So what you should notice is that if everything is within the absolutes, it is going to flip. It's going to make a reflection where the graph is not allowed to be in the negative region. So my vertex is this guy right there. So the coordinates are -2 and +4. My domain would be x such that x is an element of real numbers. So it does continue forever left and right. Our range would be y is from 0 and greater. So we would say greater than or equal to 0, YER. Okay, so these are the two that we're going to focus on, is our absolute values that are linear and then quadratic. So our piecewise function, so what I want you guys to remember is that any positive region, when we graph it, will stay the same. So I'm going to redraw this. It will stay the same. But this negative region will flip upwards and make a reflection. So it's going to reflect across the x-axis. So this guy is no more. This guy disappears, giving us the kind of that V shape. Same thing here. We have this is positive, so it stays positive when we have the absolute. But this one will reflect, and if it was 4 units below, it's going to be then 4 units above the x-axis. So our graph is going to look like that. And when it comes to absolutes, we're going to have arrows on each end because they do continue on forever. So wherever I draw the pink, that's your new graph. With a quadratic, I'm going to have this part being the same because it's positive, this leg being the same, and then this section below the x-axis, as you can see, the x-intercepts are going to be the same, but it's going to flip where graph is going to look like that. So it's kind of like a W shape approximately. We have arrows on each end because it does continue on forever. So anything below the x-axis doesn't exist when the entire thing is within absolutes. And then here, this positive region stays the same, but our negatives become positive, so it looks like that. Okay, so the blue is my new graph, and when it comes to the linear, the pink was my new graph. Our last piece is we have to be able to do piecewise function. This comes back again in calculus. So if you end up doing calculus, you'll see these piecewise functions. So we're going to express this as a piecewise function. What we want to do is we want to figure out what the x-intercepts are. That's kind of the most important thing, is looking at the x-intercepts from those two graphs. So we're going to start by looking at A, which is the absolute, so y equals the absolute of 3x plus 2. And B is we're looking at y equals absolute of 4 minus x. So what we want to do is find the x-intercepts first. So we want to take what's inside the absolutes and make it equal to 0. So we want to solve for x. So our x-intercept is negative 2 over 3. It only goes through the x-axis once. Once we find the x-intercept, I'm going to sketch what this looks like. It doesn't have to be perfect. I just want to graph approximately what I'm looking at. So I know that this is an increasing graph where my x-intercept is at negative 2 over 3. So if this is 1, we have 2 over 3. And we're increasing our graph. So this is what the graph is going to look like. So what I want to remember is that this graph is going to stay the same. This part of the graph is going to stay the same. So if I were to remove those absolutes, it would not change. So when we're talking about piecewise functions, we start off like this. We say 3x plus 2. So if I were to remove those absolutes, that remains the same. So that would be to the right of that x-intercept. The right of the x-intercept is always greater than negative 2 over 3. So when we want where the graph is greater than 2 over 3, so that's the part of the graph that will give us that V shape. So that remains the same. But what we also need to remember is that this part of the graph, the bottom part, flips upwards and then will go like that. So that would be a reflection. A reflection will be where we have negative of that equation. So that means we distribute the negative and it becomes negative 3x minus 2 to get that purple image that I just tried to draw. And that part of the graph is represented by x less than negative 2 over 3, meaning to the left of this x-intercept. So we kind of divide the graph into two pieces, which is why it's called a piecewise function. The left is the negative of the graph, meaning the flip of it, and the positive, the graph that stayed the same, was to the right of that x-intercept. And this is our answer. So this is what makes our V shape. So if we use that purple and then that circled part that I circled in red, that will create my V shape of my absolute. Let's look at the next one. The next one is 4 minus x, which is a downwards graph, and we want to find the x-intercept by making it equal to 0. Then we're going to bring that over to become positive, so x is positive x. When we bring it over, negative x becomes positive x, and we get 4 equals x. That's our x-intercept. So 1, 2, 3, 4. We want to graph that. And this is a downwards facing graph because we have negative x, so we have something approximately that looks like this. Okay, so as you notice, the part that stays the same would be to the left of that x-intercept, so this part stays the same. So when we're doing piecewise functions, we would say y such that 4 minus x, the part that stays the same, meaning when we remove the absolutes, it will be to the left of that x-intercept. So where x is less than positive 4. And then 4 minus x, we want to say where x is the other opposite. That would be where this guy flips upwards. So what we would have to do for this one is we would have to take this piece and flip it upwards, and by doing that it becomes the opposite, meaning the negative of it. So we make 4 negative 4 minus x, and it becomes x is greater than 4. That's to the right of 4. So we want to also, for both of these graphs, we need to put the equal sign under one of these inequalities. It really doesn't matter which one, but the reason we do that is because we can't have the graph not going through and including the x-intercept. So we need to include that x-intercept. So we want to say x is greater than or equal to -2/3. So that includes that x-intercept. So there's not this so there needs to be a point that it continues on. So there should be an equal sign for both of these equations, but only one of the inequalities. Okay, and that is the piecewise function. Example number 4. We're going to start by graphing 3x plus 1. So 3x plus 1 would look like, if you were to remove the absolutes, it would be a positive graph. We need to find the x-intercept. So that would be the x-intercept of the first one would be -1/3, because you would make 3x plus 1 equals 0, and then you would bring the 1 over and divide by 3. Here, you would take x squared minus x minus 2, make it equal to 0, and factor it. So that would be x minus 3 and x, actually, it should be x minus 3, x minus 2, and x plus 1. Okay, so you want to factor that, and it's x minus 2 and x plus 1. So once you have it factored, you want to solve for it. So you'd say x equals +2 and x equals -1. That's the x-intercepts that you're going to get from that one. Okay, so we're going to plot those, 2 and -1. And this one we have -1/3. We know that this one's an increasing increasing graph, so we're going to do that. That's the linear equation if we didn't have absolutes. And then here, the parabola that we're getting is an upwards parabola. So I'm just sketching it. It's not perfect. It's just kind of to give me an image of what I need, right? So when I'm creating my absolute, I also want to find the y-intercept. So the y-intercept for the first one is if you make x equal to 0. So if you make x equal to 0, you'd get 0 plus 1, and the absolute of 1 is 1. So the y-intercept is 1. And the y-intercept for the other one, again, we would make x equal to 0, so it would be 0 squared minus 0 minus 2 in absolutes. That would be -2 in absolutes, which is 2. So the graph is going through +2 once we have the actual absolute graph. So like this one's going to look like this, because it has to be that V shape. This one, the arms that are going upwards and above the x-axis are going to stay the same, but this one is going to have that kind of loop, that parabola piece that flips up. It's going to go above the x-axis. So the orange is going to be my absolute graph. Now, when we're creating our piecewise function, we would say y equals, and then we have this set bracket that says that the graph that was positive, meaning 3x plus 1, the piece that stayed the same was to the right of it. So the right of the x-intercept would be x is greater than or equal to -1/3. And then the part that I had to flip was to the left of that x-intercept. So -3x minus 1, you're just making the values the negative version of it. And that's going to be where x is less than -1/3. That's the left of this value right there. The piecewise function for b would look like this. So we would have x squared minus x minus 2. So the pieces that stayed the same was this and this. So for the x-intercept of -1, we had to go to the left of it. So we know that the value we care about was x is less than or equal to -1. And we also needed the part where x was greater than or equal to 2. So because we wanted the right of this one and the left of this one. So that's how I write those values in. Okay, and then the negative version is where I make everything opposite signs. So -x squared plus x plus 2. So that's the negative version of it. All the signs change. That would be in between. That's the part that I had to flip. So it went from from upward facing to downward facing. So that's the part in between. So x was in between, but not equal to. So in between -1 and in between and less than 2. So what that's saying is the graph I cared about was greater than -1, but less than 2. Okay, so that's what the piecewise function would look like. The domain for all of them would be x such that x is an element of real numbers. So that would be for A and B. The range for the first one for A would be y such that y is greater than or equal to 0 YER. So the graph is from 0 and up. And for the second one, it would actually be the same as well. So it would be from 0 and up. So both of them would have the same domain and the same range. And in example number 5, we want to find the piecewise function again. So I start by finding just within the absolute, I would make that equal to 0. You need to find the x-intercept. And in this case, the x-intercept is going to move up by 4 because of this. So x equals 3 is going to be where that line is that the graph is going to change from there. So I know that if I were to graph this, the absolute of x minus 3 plus 4, I'm going to show you how to do that in your calculator. So I'm going to do this next example in the calculator just to show you what that looks like. So you're going to go to Math, to the right to Number, and then press number 1. And it'll give you this. And inside the brackets, you're going to go x minus 3, and outside the bracket, you're going to go plus 4. You're going to graph it, and as we can see, the graph splits and changes directions. It goes downwards and then changes to upwards when we hit that x equals 3. So we're going to sketch that. So this happens at x equals 3. So when we create our piecewise function, it's going to look like y equals. The first version doesn't change, so we're going to go x minus 3 plus 4. The side that, in this case where x was positive, that would be where the graph is going up to the right. So that would be to the right of 3. So that's where x is greater than or equal to 3. And then the negative version of it is where I change all the signs around the absolute. So nothing else changes except the x and the -3. So this becomes positive 3, and then plus 4 is not within absolute, so don't change that value. And that would be the graph that, this is where x is negative, and x is negative is where the graph goes downward. So that would be this part right here. So that's where x is less than 3. As you can see, I only put an equal sign for the inequality for one of them, not both. And also what I'm going to do is simplify. Minus 3 plus 4 is equal to x plus 1. So I'm going to simplify that. And the second one, negative x plus 3 plus 4 is plus 7. So we do want to write it out as that. So those would be my piecewise functions. Our next one, we're going to sketch that first. So we're going to go Math, number 1, absolutes, and inside the absolute you're putting everything in. Okay, so we will have to change the window a little bit. So the Y height, we're going to go up to 20. As you can see, it looks like this. So this is what I should be seeing when I graph it. The x-intercepts are important. You need to find those. One's going to occur at -2 and the other one's going to occur at x equals 4. So the x-intercepts for B, x-intercept was -2 and 4. So when I sketch it, it looks like that. So when I create my piecewise function, we look at 2x minus 1 squared minus 18. This is going to be the graph that is upward facing. So that would be these legs, because those are the legs that are for upwards facing. So that is going to be represented by the left of -2 and the right of 4. So x is less than -2 and x is greater than 4. Also, it has to be equal to those values. And then 2x minus 1 squared, we're going to put a negative in front of the 2, and we're going to change -18 to +18. So that's making the opposite sign of that. That's the reflection of that image. So making the negative in front of the 2 and the 18, that distributes it to everything. So as you can see, when your a value is negative, that's going to be a downwards parabola. So that's going to be represented by that middle section where x is between -2 and 4. So when x is between -2 and 4, we have a downward facing parabola, and this is our piecewise function. And our last one, C, we have a parabola again. So when we graph it, if you were to find the x-intercepts, the x-intercepts should actually occur at -5 and +1. If you were to make it equal to 0 and solve for the x-intercepts, so that's going to give us an image like that. So when we create our absolute values, our piecewise function, we're going to have -x squared minus 4x plus 5. That's the middle part because that's a downward facing parabola. So that's going to be where x is less than x is greater than -5, but less than and equal to 1. So that's the in-between region. So that is represented by this part right here. And then our last section, when we have the positive version of it, we're going to change all the signs here. And that's going to make it the positive version. We're going to have the graph that looks at this part right here and that part right there. So that means where x is less than -5 and where x is greater than 1. So we don't put them as one inequality like above, because these are two separate sections that aren't connected when we look at the pieces. So we're saying where x is less than -5 and x is greater than 1, that would be this and that. And that's how we get the completed image of the absolute graph. So that would be our piecewise function. Okay, so that's it for lesson 7.2.